efforts. Let me shortly introduce myself. My name is Daniel Swimmer. I'm from Germany, especially at the University of Bonn. The topic of my talk is microstructure, activity properties, and damage mechanism of aluminum silicon cast alloys. The content of my talk is I'll give you a short introduction, why I make this thesis, what kind of materials did we use, and what kind of experimental work have we done. I will show you some results and give you shortly a short comment. So, what's the motivation of my talk? I think most of you know that aluminum silicon cast alloys are widely used in automotive engines like engine blocks or cylinder heads. You can see on the right hand side in the picture. So the main positive things of aluminum cast alloys are they are good castability and a good thermal conductivity by a high specific strength. But if you watch the picture on the left hand side, you see that the specific power and firing pressures of the engines is still rising, and we need to do some efforts to create new aluminum silicon cast alloys with better improved mechanical properties at high temperatures, for example, better creep resistance or better high cycle behavior at higher temperatures. And what can we do in this case? We can addition of strengthening elements like copper, nickel, and or magnesium, so I get enhanced properties at higher temperatures, for example, creep and high temperature mechanical properties. So, what kind of material did we use? I want to simplify it. Okay, we have our base alloy. It's a commercial A354 alloy with 78% of silicon and 0.5% of copper and 0.4% of magnesium. That's our base alloy. Based on this alloy, we change our elements like copper, nickel, and magnesium. For example, in alloy number 2, we had addition of 1% of nickel. In alloy number 3, we had an addition of In alloy number 4, we had an addition of copper, nickel, and magnesium, and based on alloy number 4, we have further addition of copper, nickel, and magnesium. All alloys are refined with strontium and grain refined by titanium. So after that, we did a T6C treatment by solution annealing, quenching, and artificial aging. With this temperature, you can see here in this table the modified alloy that reduced solution annealing to prevent incipient melting of some intermetallic phases. So let's have a short look at the microstructure after T6C treatment. We have a normal microstructure. Most of you know it. We have our aluminum matrix. We have our alpha phase, which contains iron and magnesium and silicon. We have our tectic silicon with a globular shape. If we add nickel to our base alloy, we get more intermetallic phases. For example, the eta phase, which contains aluminum and nickel, the T phase, which contains aluminum, iron, and nickel, and the Mg2Si phase. A further increase of copper, nickel, and magnesium leads to complex microstructure. You can see on the right side. We also have the T phase with iron and nickel. We have the delta phase, which contains copper and nickel and aluminum, and also silicon precipitates and Mg2Si precipitate. Here in the last picture, we have our high alloy which contains the Q phase. That means we have a phase with copper, magnesium, silicon, and aluminum. Also the delta phase, and here some other phases again. These alloys are also strengthened by solid solution strengthening, for example, magnesium and copper, and secondary precipitates like the theta phase, the Q phase, or the beta Mg2Si phase. So, what kind of setup did we use? We did a low cycle fatigue test and a servohydraulic testing machine and an MTS 810 with this specimen. The specimen are polished in our gauge lengths. The temperature was applied via an induction coil, and the temperature measurement and control was done by a nickel chromium nickel thermocouple, and the tension was measured by an axial high temperature excentrometer. The tests were strain controlled at a temperature of 250 degrees. The samples were, before they were hot isostatic pressed, so we can compare our materials to, then we did our T6 G6C treatment. We did a pre-aging at 250 degrees for 200 hours in a stable microstructure. That means that our alloys are very overaged. So and we did strain control fatigue test in the range of 0.15% to 1% total elongation at a fixed strain rate and an R ratio of -1. So let's have a look at the hysteresis loop at NF half. Here we have plotted stress versus strain, and we see here in our reference alloy at 0.15% we also have plastic amounts of strain, and the total strain amplitude of 1% we have a huge amount of plastic and elastic strain, that we can say that in all strain amplitudes plastic deformation is found, and we have a huge opening of our hysteresis loop. For example, in the nickel-containing alloy, we have more stiff behavior compared to our reference alloy. That means the A modulus is much higher than, a bit higher than in our reference alloy. We have higher maximum and minimum stresses, and we have a slight higher hardening in our nickel-containing alloy. If you watch at the stress amplitude versus the number of cycles, we can see here that for all total strain amplitudes we have cyclic softening. In this line where our total strain amplitude is 0.15%, we have in the beginning first cyclic hardening, and after 10 cycles until failure we have cyclic softening. The cyclic softening is more pronounced at higher strain rates. If we compare this with the alloys, we have here a black one, our reference alloy, for 1% total strain amplitude. We have here a higher delta sigma stress amplitude in comparison to our reference alloy. So that's you can see here. And we have in all three alloys we have cyclic softening. So we have also a higher delta sigma in our modified alloys in comparison to our reference alloy. If you remember at the microstructure, we can see here we did some EDS measurements, and in contrast, they are the typical phases. You see the red one is our eutectic silicon phases, and our blue one are our nickel-containing phases. And what we see here is that the nickel-containing phases are near the eutectic silicon and stabilize the microstructure, and that's the reason why we have a higher stress amplitude compared to our reference alloy. If you watch our fatigue life diagram, you see here the total strain amplitude versus the number of cycles in a double plot. We see first of all for our reference alloy with decreasing strain amplitude you get high number of cycles to failure. In comparison to our alloys, we see here that we have a comparable fatigue life between these two alloys. At higher number of cycles to failures, we have higher fatigue life in comparison to our reference alloy. The same behavior is at the other two alloys. In our copper nickel magnesium containing alloy, we have slight decrease in low cycle fatigue regime, and a similar behavior compared to the nickel containing alloy in a high cycle fatigue regime. If we watch at the surface in LCF regime for example for two alloys at a total strain amplitude of 0.4% at about 5,000 cycles to failure, we can see here ductile behavior of our aluminum matrix. We see broken eutectic silicon, and also with these errors we can see decohesion between the matrix and eutectic silicon. In our nickel containing alloy, for example, at 0.25% at a fatigue life of 12,000 number of cycles to failure, you can see here in the BSE contrast that we have here our intermetallic phases which are broken, always the short direction. That means precipitates which are orientated parallel to the loading axis are always broken the short way, and the same way as when the intermetallics are orientated perpendicular to the axis, the short track always vertically. Always we have fatigue tracks in our eutectic silicon, and also the ductile behavior in our aluminum matrix. In our copper nickel containing alloy, for example, at a total strain amplitude of 1.0% and a number of cycles to fatigue of about 700, We have also a ductile behavior of our aluminum matrix, and we have a D-cohesion between aluminum matrix and our eutectic silicon, and a huge damage. And if we watch in the BSE contrast, where we can see our different intermetallic phases, we can see here huge cracks in our intermetallic phases, and a network formation, and we are seeing huge secondary cracks, which is the reason why we have significant cyclic softening, especially at higher strain amplitudes. So now in the end, I want to give you a short conclusion. So we have seen that the microstructure in aluminum silicon castanoids can modify by several elements like copper, nickel, and or magnesium, and leads to a complex microstructure. With the formation of a stable skeleton structure, we have seen that we have cyclic softening at all strain amplitudes and in all alloys. We have higher stress response due to the microstructure in our modified alloys, and we have a ductile behavior of our aluminum matrix and more brittle behavior of eutectic silicon and intermetallic phases. Thank you.
Thank you very much.